There's a lot of familiar faces. I have seen many of you in many different institutes and during different times of visit. Can you all hear me? Okay. I feel comfortable developing things on the blackboard, but linear algebra is something which is prerequisite. So what are the prerequisites for data assimilation? Linear algebra, probability and statistics, optimization theory, multivariate calculus, good facility with programming. Why am I mentioning this? I want each of you to calibrate yourself against these requirements. If you have difficulty, is this difficult? It is not simply enough to say I have difficulty. You have to tell, I have difficulty in programming. I have difficulty in probability theory. I have difficulty in optimization theory. I have difficulty in multivariate calculus. You need to be able to bring it down to that level of detail to be able to go over all the details. How many of you are PhD already? Raise your hand, guys. Be proud you're a PhD already, right? Good. How many of you are working for PhD? How many of you are masters, working for your master's thesis? Raise your hands, please. Okay. Is there anybody who doesn't know linear algebra? How many of you know linear algebra? It's a complimentary question. Come on, guys. You guys didn't raise your hand for anything. Huh? Yeah. Well, how many of you have done linear algebra? You may not remember. If you got a master's degree in India, you cannot have escaped linear algebra. Why? I had all my education in India. I'm an Indian social science product, so I know Indian education system very well. All of you must have done probability theory, statistics, linear algebra, may not be multivariate calculus, may not be detailed optimization. I'm sure everyone should be a good programmer. How many of you believe you are good programmers? You don't have confidence in your own programming ability? Come on, guys. That's right. You have to be known for something. Yes, I'm a good programmer. Yes, I'm good in applied mathematics. You have to believe in your own self. So these are the basic prerequisites. The topic given to me is fundamental theoretical aspects of data assimilation. Because all of you know linear algebra, even though there are 2 sessions for linear algebra that is given, I'm going to go over some of the very basics in linear algebra. And tomorrow morning onwards, I'm going to mix linear algebra with data assimilation. Because doing mathematics for mathematics' sake is one thing, doing applied mathematics is another thing. I'm sure all of you are in applied mathematics. So to see mathematics being applied in a given context probably makes more sense to many of you. I'm going to tell you a particular tool, why it is needed, when it is needed, and we'll use it. That's the plan. I also want you to be interactive. I don't want this to be a monologue. Please feel free to ask questions, stop at any time. All of you? Good. So with that preamble, I'm going to start with finite dimensional vector space. What is finite dimensional vector space? Finite dimensional vector space is the basis for all of computing. Is there a model on which you base your computational problems? It is finite dimensional vector space. It is the mother of all computational problems. So I'm going to quickly talk about some of the basic properties from multidimensional vector space. So these are the notations. Capital R will be for real numbers. You are all going to get a copy of the slides. And if you want to write down, please do to C, set of all complex numbers. R to the n refers to set of all real vectors of size n. C to the n, set of all complex vectors of size n. Largely, we will deal with real finite dimensional space. There's also a corresponding complex finite dimensional space. In complex case, there is a real, so if I have a vector of size 3 with complex numbers, there are 3 real parts, there are 3 imaginary parts. So you can think of it as a 3-dimensional complex variable or a 6-dimensional real variable by collating the real part and the complex part separately. So with a loss of generality, I'm going to talk about n-dimensional real space. Vectors are listed column-wise. 0 is the vector. These are examples. This is an example of a complex vector, real vector. I is the square root of -1. We will largely deal with real vectors. These are basic operations. Small ABC are this should be R. Sorry, this should be ABC are real, XYZ are vectors, XYZ are listed as the n vectors, T transfers transpose. I have vector addition, vector subtraction. I have a multiplication of a vector by a constant. Z is equal to AX plus Y. So X and Y are 2 input vectors, A times X plus Y. So this is called scalar multiplication of a vector plus a vector. We all know all these basic operations. But what's important and interesting here is the number of operations that you will be called on to perform. Here you need n addition subtraction. Computationally, addition and subtraction is the same thing. We need to worry about complexity in terms of amount of work to be done. So to be able to add 2 vectors, you need to perform n operation. You need to be able to add a scalar times a vector plus a vector. You have to do n multiplication and you have to do n addition. The total number of operation is 2n. This operation is also called SAXP. What is SAXP? Scalar times a vector plus a vector. It's a standard operation in numerical linear algebra. Now I'm going to tell you the basis for the vector space. For something to be a vector space, it has to satisfy 3 conditions. So V denotes a set or collection of real vectors of size n. Under what condition does this set become a vector space? Not every collection of vectors become a vector space. Vector space is also called linear space. Sometimes it's called linear vector space. I will simply use the term vectors. So there is an operation. So what are the basic operations? Vector addition. Addition subtractions are essentially the same. So if I say addition, I also mean subtraction, scalar multiplication. So these are the only 2 operations. Vector addition and scalar multiplication of a vector by scalar multiplication of vector by a constant. So what is the property? This set, if I pick any 2 vectors, the sum must belong to that. That's called closeness. If you add 2 real numbers, you get a real number. If you add 2 complex numbers, you get a complex number. So this property is called closeness under operation. And that is very fundamental. Because by doing certain operation, I should not get out of that set. Are you all with me, please? I hope you understand what closeness is all about. And what is the next one? If you give me 3 vectors, if I want to add, addition is a binary operation. I can add only 2 numbers at a given time. So if I am given 3 objects, I have to add x and y. To the result, I have to add y. I can add y and z. To the result, I can add x. So if these are essentially the same, that's called associativity property. Associativity is very fundamental. Why? Without associativity, life will be miserable. What is associativity tells you? If I have a bunch of numbers, whichever order I add, the result is the same. How many of you do shopping? These days, there are supermarkets everywhere in India, right? So you take a cart, fill your cart, and you put everything at the belt. Do you really care the order in which the secretary is adding to find the total? No, you are talking to somebody or who is checking such thing. Why? So long as there is no error in the entry of the price, whichever way you add, the sum is going to be the constant. Think for a moment. You buy 10 items. If the order in which you are going to add is going to decide the sum, how many ways in which you can order 10 objects? Factorial 10. What is factorial 10? It runs in millions. You will still be in the shop. What is my place? So associativity is very fundamental to life. Without associativity, life will be miserable. The order is of no consequence when I'm trying to add a bunch of numbers. And it contains a special vector called zero vector. And what's the property of zero vector? You add 0 to any number is 0. You add a 0 vector to any vector, that is 0. Then for every vector x, there is a vector y such that x plus y is equal to y plus x is equal to 0. So y is called the additive inverse of x. 3 minus 3, 7 minus 7, minus 7 plus 7. So every vector has an additive inverse. When you add a 0 vector to every vector, the vector remains the same. Associativity property holds good. Addition, the set is closed under addition. Such a set has to be an infinite set. A finite set cannot possess this number, cannot possess this property. So for a vector space that to be, it has to be an infinite set of vectors. That's the first thing. Mathematically, any set that satisfies these four properties is called a group. It has an algebraic structure called the group. Then, so this talks only about the addition. This talks about the scalar multiplication. Please remember, I told there are only two operations, addition and scalar multiplication. A times x. So if you take any vector, multiply by a constant, you get a vector in the same set. And if you have two numbers, a and b, how do I multiply ab times x? You multiply ab, you get a real number, and then multiply that. And 1 is a unique number, real number. If you multiply any vector by 1, you get the same vector. You get the same vector. So that's the property of number 1. That's the property of number the vector 0. And then the distributivity property. A times x plus y is ax plus ay. A plus b times x is ax plus by. This is for all x and y and for all real a, b. Any set of vectors that satisfies these three is called a vector space. And this is the basic foundational property. You can think of rewriting programs where you want to use distributive property, you want to exploit associative property, so on and so forth. So it is this that provides the basis for everything that we do in all of sciences that relates to computing. So what are the examples of vector spaces? Here, the set of all real numbers satisfies all these axioms. R to the n satisfies all the axioms. C to the n, complex vector space. So even though I call it vector space, the word vector in vector space is only a placeholder. The set of all matrices that forms a vector space. The set of all polynomials forms a vector space. The set of all infinite sequences that are square summable, that also forms a vector space. The set of all continuous functions in the interval AB is a vector space. Hey, that's the reason why this is basic, quite basic. So vector space comes in various shapes and forms. Because we start with the definition of vector, we still call it vector space, but some authors call it linear space, linear vector space. So linear vector space, the name vector is simply a placeholder. I can replace the vector by matrix, by polynomials, by functions, by infinite sequences. So vector spaces arises in various shapes and forms. Now I would like to be able to introduce newer operations. Okay, now let's see. What do mathematicians do? What is mathematics? Every branch of mathematics starts with the basic set. And then I'm going to define operations that are consistent with the properties of the set. And mathematics then develops an algebra. Then they develop an analysis. What is algebra? Matrix algebra, polynomial algebra, vector algebra, tensor algebra. Are you all in my place? Algebra is algebra. What is that? What is the elements on which this algebra is being done? Real numbers, vectors, complex quantities, polynomials. Everybody? That's a unity in the mathematical formulation. So I need to be able to define operations. Each universe, the real system, the complex system, the vectors, the matrices, the polynomials, they all have operations specific to the properties of that particular system. So I'm now going to quickly talk about vectors, that operations that are based on vectors. X, Y, Z will be vectors, A, B, C will be constants. I'm going to use this symbol, bracket symbol. It has two inputs. So bracket xy is called the inner product. So if you give me two vectors, I produce a scalar. The scalar is called the inner product or the scalar product. The inner product of x and y is the same as the inner product of y and x. That is called the symmetry property of that. What are the properties of the inner product? The inner product is always is zero only when x is zero. The inner product is symmetric. The inner product is additive. If you multiply a vector by a, the inner product gets multiplied by the same vector. I can multiply x by a, y by a. If two inner products, x with z and y with z, they are equal for all z's, then x must be equal to y. That's again a property of the inner product. The inner product in the case of complex is inner product. If x and y are complex vectors, the inner product is not xi, yi, it is xi, yi bar. Bar refers to the complex conjugate. But in this course, how many of you have dealt with complex numbers in data assimilation? We generally don't. We don't formulate the problem that way. But I want you to understand that the complex vector algebra, real vector algebra, there are parallels between the two, but I have to adapt the definition suitable for each space that we are talking about. Then there is an operation called outer product. So if you give me two vectors, a row times column, that's scalar. A column times row is a matrix. So a column times row is called the outer product. The row times column is called the inner product. So you give me two vectors, I can produce a scalar or I can produce a matrix. The scalar product, which you already saw, this is the x is a column. All vectors are column vectors. If I want to get a row vector, I'm using transpose. So this is x, y. So what do? I multiply every one of them by x1, I get the first row. I multiply this row by x2 and get the second row. I multiply this by the xn, I get the nth row. Outer product matrix. Inner product of two vectors. Outer product as an operation. Inner product as an operation. Scalar multiplication as an operation. Vector addition is an operation. Vector subtraction is an operation. So I'm trying to enrich the tools of operation with respect to my linear vector space that consists of n-dimensional vectors. That's what we are talking about. So you can see the outer product can be looked at. It is a multiple. See, the first column is the multiple of the vector x by y1, multiple of vector x by y2, the multiple of x by yn. Or I can think of it as first row multiplied by x1, second row multiplied by x2, third, the last row multiplied by xn. Outer product, inner product. How many of you knew outer product so thus far? To how many of you this is new? Come on, guys, you have to raise your hands for one question. They are complementary, right? How many of you knew vector outer product? To how many of you this is new? One of the fundamental aspects of learning is, before I came to the class, I did not know, now I know. You have to keep on incrementing your knowledge. So there is nothing wrong in admitting, I did not know then, now I know. That's incremental learning. Are you with me, please? I will keep asking you these questions like that. So never hesitate to say, I did not know. Never hesitate to say, I did not know, but I know it. So how many of you now know? That's right. That's right. Good. With respect to numbers, how do you tell the size of a number? Absolute value. With respect to vectors, I need to find a size. The vector has large numbers, but I want to be able to succinctly represent the size of a vector by a scalar. I want to be able to succinctly represent the size of a matrix by a scalar. That's what's called the norm of a vector, the norm of a matrix. How do you measure the size of people? One way, height, weight. Another way by education. Another way by marital status. We have several attributes, right? We use different attributes for different purposes. Are you with me? So for vectors, I need to be able to represent its size. When it's a question of numbers, there's only one way, absolute value. Strip the sign, you get the number. But when it's a question of vectors, there are several ways of measuring the size of a vector. Let's talk about weight. Weight can be measured in terms of different units: pound, kilogram, distance, kilometers, miles, temperature, centigrade, Fahrenheit, absolute scale. The object is one, the scales are different. Are you all with me? So temperature can be measured in terms of absolute scale, Fahrenheit scale, as well as centigrade scale. So the size of a vector, likewise, can be measured in various ways. One is called the Euclidean norm, that comes from the basic Pythagorean theorem. All of you with me, please? Come on, guys, keep nodding your head. It's good for you. Why? We all had a good lunch. I don't want anybody to doze off. So I don't want your head to doze off because you are sleeping. I want your head to doze off because, yeah. Are you all with me? Okay, good. So Pythagorean theorem essentially tells you to measure the size of a vector, which is the norm of a vector, which is the square root of the sum of the squares of the component of x. Everybody? Then that's called the Manhattan norm or a one norm. Why that Manhattan norm or one norm is interesting. Suppose I'm driving through a city, I have to drive by a car. You go east, then take a left, then go north, then go south. So I need to be able to add the total distances I travel. I have an electronic chip. In an electronic chip, there are different functional units. I need to be able to connect them. When I connect these different functional units, I use precious metal like gold, silver as a connector because I want the resistance to be much less. So I want to be able to find out what is the total length of the wire that is needed to be able to make a chip work. Manhattan is a city in New York, is a city in New York City. So it is also called taxi cab distances. So it is the sum of the absolute values of the components of the vector. Chebyshev norm, Chebyshev is a Russian mathematician, is a maximum of the absolute values of the components of that. Then there is a Minkowski norm, which is called also P norm. So I refer to these norms by a subscript: 2 norm, 1 norm, infinity norm, P norm. What is the P norm? It is the pth root of the sum of the pth powers of the absolute values. When P is 2, I get the Euclidean distance. Then there is a last one is called the energy norm, where A is a symmetric positive definite matrix. How many of you have heard of all these norms? How many of you, everyone should know Euclidean norm. So what is Euclidean norm? It's a crow's flight. One norm is essentially by car. Infinity norm is the maximum of the components of x, absolute value of the components. Pth norm, you take the pth power of the absolute value. Pth norm is a generalization. Then normally, we would use these in high-level mathematics. Sometimes they use P norm. We will also have occasion to use in data assimilation the symmetric, the energy norm. Why it's called energy norm, we'll come back to that at an appropriate time. What's that? Why not? Why not? Why centigrade? Why Fahrenheit? Why absolute? Are you with me? In America, we still use miles. Here you use kilometers. There are ounces and pounds. You use kilograms. Why not? It works, so long as there is a table. Good question. Why? In mathematics, when you try to prove theorems, certain proof of certain results using certain norms becomes a lot easier. So what do mathematicians do? I'm not going to pull my hair to prove a theorem in a particular norm. I will prove it for any norm that is convenient to me, but then I will show all these norms are equivalent. So what does it mean? If I can show all these norms are equivalent, proving any result in one norm can be translated to any other norm, so that frees you up by being tied to one particular norm. Are you with me? That's right. You can generate your own norm. So that's a freedom to do mathematics. That's the idea. Any other question, please? Okay. So if I have a norm, then I have a notion of a distance. How far, well, let me finish the distance. How far Bengaluru is from Madras? By flight is shorter. By road I can measure using one norm, infinity norm or energy norm, whatever way you want. So, once I have a concept of norm, I have a concept of distance. So I have a 2 distance, 1 distance, infinite distance, p distance, energy distance. The question why is interesting. Why? Ultimately, I have to prove results using mathematical techniques. Whichever norm is convenient to me to be able to prove a result, I will use it. If I know that all these norms are equivalent, in fact, it's the proof in linear algebra that all these norms are equivalent. Okay, I thought you had a question.
Sir, later I will ask.
Oh, good, good. But don't compromise on asking questions, though. So what is that to be a norm? Yeah, go ahead, I'm sorry. Okay. Okay, energy norm is substituted by A. A is a matrix. So X transpose AX is called a quadratic function. You know that? We are going to talk about that. So look at this now. A is a square matrix. There's a row, there's a matrix, there's a column. So a row times matrix times a column is a scalar. Got that? That's right. And then take the square root of that. When she nodded her head, I have a particular anecdote I need to tell. I got my PhD in 1973. I've been teaching continuously. This is the 51st year I've been teaching. I went to the United States in 1975 as a postdoc. When I went to America, my mentor will ask me questions. I used to answer him typically by nodding my head, yes, sir, yes, sir. Then he asked me, Varahan, stop. In America, this is for yes, this is for no, but you say this. Don't in India we do all of that? When I saw you, I'm sorry, I'm not criticizing you, I was reminded of that. So this is for yes, this is for no, this is I don't know, you are everywhere. Good. Very, please keep asking questions. Are you all with me? You got the idea of what the energy norm is now? So the value of this energy norm depends on the properties of the matrix. So if you chose the matrix in an appropriate way, this satisfies all the conditions for the norm. We'll have more occasion to talk about that. So norm distance. Now, that brings us to the following question. That follows the question, why so many norms? Can I create my own norm? What is that to be for something to be a norm? It gives you freedom. So I want to be able to gain that freedom. So you can create your own norm provided you satisfy these properties. What are that? A norm is a function that maps vectors into scalars. That's called scalar valued function of a vector. Nx is called the norm of x. Norm is a measure of the size. When x is 0, the norm must be 0. When x is not 0, the norm must be positive. Are you with me, please? What do you mean by a vector being non-zero? It has n components. At least one of the components must be non-zero. If one of the components is non-zero, the vector is pointing away from the origin. If all the components are zero, it sits at the origin. So the norm of a vector that sits at the origin is 0. The norm of a vector that doesn't sit at the origin but points outward is always positive. The norm is a positive quantity. Norm is a homogeneous function. If you multiply a vector by a constant, the norm gets multiplied by the absolute value. If you have a vector multiplied by 2, it becomes too long. If you multiply a vector by -2, it becomes too long in the opposite direction. The length of the vector gets multiplied by the absolute value, the constant you multiply with. Then the third one is the most important thing. It's called the triangular inequality. We all know in basic geometry, the sum of the two sides is always greater than or equal to the third. That's the first theorem we learn about triangles. When do we learn that? 8th grade. If you didn't do it by 8th grade, it's too late. Two-dimensional Euclidean geometry is where we learn all these basic things. Are you with me? So any function you define that satisfies these three must be a norm. So it's a homework problem now. Show that the Euclidean norm satisfies this. The one norm satisfies this. The infinity norm satisfies this. The P norm satisfies this. The energy norm satisfies this. If it were to be a linear algebra class, I will ask all of you to be able to take this a homework problem, but it always worth it for you to be able to attempt it. All of you, please check it out. So that's how you are going to build your mathematical powers. Oh, I'm sorry. Oh, sorry, I'm going the wrong direction too fast. Yeah. The 2 norm has a very special place. 2 norm is intimately associated with the scalar product. 2 norm is the only norm that is related to the scalar product. Verify, this is a homework problem for you, verify, this is called a parallelogram law. If I have two vectors, x, y, then you can complete the parallelogram. Are you with me? So you have the norm square of x plus y, the norm square of x minus y, that is equal to 2 times norm square of x times norm square of y. This must be y. All of you? I want you to check that. And what is the definition of a 2 norm? The 2 norm is essentially inner product vector itself. So 2 norm is derivable from inner product. 2 norm is the only norm that is related to the inner product. So 2 norm and inner product, they always go together. That's what Euclidean geometry is all about. That's what we have been introduced to, the plane geometry, when you're doing 7th grade, 8th grade geometry. When you do 7th grade, 8th grade geometry, you don't prove anything. You simply, they state the facts and you repeat it. That's all right. That's how you learn first. That's how you learn first. Are you with me? I'm not going to keep asking questions, but please, if you think I'm going fast, please ask a question.
Sir, can you go back, please? The right-hand side.
What's that?
Right-hand side.
This must be y. That's a typo. That's right. I already mentioned it. It's a typo. Good, thank you. Okay, now that's called the unit sphere. So what is that we are talking about? Sphere. Sphere means a ball. So the unit sphere in 2 norm looks like this. But the unit sphere in 1 norm looks like this. Unit sphere in infinity norm looks like this. The unit sphere in energy norm looks like this. Let's talk about that. 1 norm first. So if I have if I have my x in R2, x is equal to x1 plus x2. I want my 1 norm to be equal to 1. That's a unit norm, everybody. So what is this? This is equal to absolute value of x1 plus absolute value of x2. So if I have This is x1, this is x2. What is the equation? x1 plus x2 is equal to 1. x1 plus equal to 1. Absolute value, absolute value, absolute value. So I still call it sphere. But our condition, our conditioned sphere means round ball. So what is a sphere? Sphere is a locus. So your unit sphere is a locus of points at unit distance from the origin. And what is the keyword? The distance. How do you measure the distance? Two distance, one distance, infinite distance, p distance. All of you? Come on, guys, nod your head. This is for us. This is for no. And it's always good for your neck. Keep doing exercise along with your learn. How many of you have been now? The notion of a unit sphere. To how many of you this is new? Good. You're learning something. That's the idea. Okay. This is called an ellipse. It can be shown that this function represents an ellipse. So what is the unit distance? It is the locus of all points x in the two-dimensional plane that makes x transpose ax is equal to 1. So when A is a diagonal matrix phi 1, phi x1 square plus x2 square, it is an ellipse whose equation is this. How many of you know programming? I already told you, you must be an expert in programming. So what is an exercise for you this evening when you get bored? Try to plot this. All of you? Please check. I have already checked this. You already know this. Please check this. Homework problem, homework problem. All of you? Come on, guys. I will be happy to discuss homework problems sometime. I would like to encourage you to work the homework problems, come back with questions. All of you? There's a saying, the proof of the pudding in its eating, right? If you can eat your own meal you cooked, that's good, that's good. So you should be able to check your own answers. So please take these things seriously. You're all here to learn. The learning has to be tested against your understanding, and that you do by homework problems. Good. Here comes the equivalence of norms. So these are the standard inequalities between the norms. So if I proved certain theorems in certain, look at this now, 1 norm, 2 norm, they're all related by this. Proving all these things will take a 1 semester course. I'm going to devote 1 lecture. All of you? That's right. But what's the take-home message for people? You may say, hey, I'm not in mathematics, I'm in data science, I'm in environmental engineering, I'm doing this and that, but you should be aware. You should be aware of these. So you can pick any one norm in doing any analysis. That's the freedom that you get that we talked about. Now I'm going to talk about what's called functionals. What is a functional? A functional is a mapping F from the vector space to the real line. So let's talk about the functionals which we already know. All the norms are functionals. Why do we need this? Because when you read papers, they will use bombastic language. When you read papers, you want the reviewer to know that you know mathematics, right? Everybody please? But for a novice, how do you read a paper and learn things from? So what is a functional? Yeah, mapping F from V to R. So what, if f of x is equal to n of x, then n is a norm, that's a functional. That means I'm associating a number with a vector. Any association of a number with a vector is called a functional. A functional can be a linear functional or a nonlinear functional. Under what condition do I say a function is linear? If I give, sorry. Oh, I think I skipped one. I'll come to that in a minute. Yeah, functional. So what is it there? If I give two inputs, sum of two inputs is equal to the sum of the two. F of x1 plus x2 is f of x1 plus f of x2. If I multiply the input by a, the output gets multiplied. The first property is called additivity. Second property is called homogeneity. Any functional that satisfies these two properties, they are called linear functional. For example, what is an example of a linear functional? Look at this now. Let's fix a vector A. F of A of x is inner product of A times x. So when A is fixed, this is a function of x. So for a fixed A, the functional f of A of x is inner product of A with x. That's a linear functional. What's an example of a nonlinear functional? The norm is a nonlinear functional. What is another example of a nonlinear functional? For a given matrix A, 1/2 of x transpose AX. Why 1/2? Why not? I can multiply a function by any number you want. I simply, for the sake of argument, I multiplied that x transpose AX is a nonlinear function. A functional is something that converts a vector to a scalar. That can be a linear functional, that can be a nonlinear function. Do you see the difference, please? That's right. Now, I skipped another concept earlier. Vector, you have a unit vector. You define the vector divided by the size of that. Then we have the standard inequality. The inner product of xy is simply the product of the norm of x, norm of y, times cosine of theta. I'm sure you all have learned in basic geometry, right? Come on, guys. That's right. So that comes from basic geometry. Cosine theta is always absolute value less than 1. Therefore, you can get the absolute value of the inner product is always less than the product of these two. So let's draw that inequality first. So I'm not proving this, but you should know this. Please understand, inner product and the two norms are closely related to each other. This is true only for the inner product. So if I took the absolute value of that, inner product can be positive or negative. Are you all with me, please? Come on, guys. Let's talk about that now. Suppose x is a vector. This is the perpendicular to that. If y, the vector, this is the x, if the vector y lies in this half plane, the inner product x and y will be positive. If y lies in here, the inner product will be negative. I don't know where y was. So the inner product x and y can be positive or negative. It's absolute value. The norm is always positive. This is always positive. And this is always less than or equal to 1. All of it, may please? Therefore, what is one way to write this down? Cosine theta is equal to inner product of x and y divided by. So if I took the absolute value, and this being less than 1, everybody please. So I get a standard inequality. What is that? X comma y, the inner product is always less than. This inequality is one of the most fundamental and famous inequality that's called Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. What is the difference between algebra and analysis? In algebra, we talk about equalities. Left-hand side is equal to right-hand side. In analysis, we talk about inequalities and equalities. In analysis, we want to bound certain things. I may not know the exact value, but I want to know it is never more than 10. It is never less than 5. I want to be able to find bounds. So you have to ask yourself the question, what is algebra? What is analysis? What is the difference between them? When you go from algebra to analysis, You always need to learn to do with inequalities and equalities. Cauchy-Schwarz inequality is one of the most fundamental inequalities. Minkowski inequality is an extension of Cauchy-Schwarz inequality for P now. But you need to be able to make your way through slowly. How many of you have heard of Cauchy-Schwarz inequality? To how many of you this is new? Good. So norm equivalence, I have already talked about this. Functional, I have already talked about that. Now I'm talking about the notion of orthogonality. How do you measure orthogonality? The inner product must be 0. So let's talk about measuring orthogonality. So what is the difference between geometry and analytical geometry? We talked about difference between algebra and analysis. Two-dimensional geometry I can do in pencil paper. Three-dimensional geometry I can do with pencil paper. 10-dimensional geometry, n-dimensional geometry. There is no visualization. So you have to do everything analytically. So analytical geometry talks about properties of geometrical objects in high-dimensional spaces instead of using diagrams, but using algebraic techniques, analysis techniques. All of you? You need to know the basic differences in here. So orthogonality in a two-dimensional plane, I can simply say that is orthogonal. But I have a n-dimensional vector, I have an n-dimensional vector. How do you test? I can't draw them. I can't measure the angle. I go back to Cauchy-Schwarz inequality. I go to Cauchy-Schwarz inequality. So when the angle between them is 90, cosine 90 is 0, the inner product is 0. How many of you are with me? So that the inner product must be 0 characterizes orthogonality in multidimension is simply an extension of what you see in 2D. You all have an aha here? That's right. So geometry angle between the vectors is 90. That's a geometric concept, visual. That the inner product must be 0 is analytic characterization of that same property. So we have to go from geometry to analytic geometry, where I can express geometric principles analytically using examples, using expressions. So so there are two types of orthogonality. One is called conjugacy, another is called orthogonality. Orthogonality is a special case of conjugacy. So if two vectors x and y are said to be orthogonal if the inner product is 0, two vectors are said to be A conjugate if x transpose AY is 0. If I have a collection of vectors, I say they are mutually orthogonal if for any xi, xj, the inner product of xi with xj, j not equal to j is 0. When I is equal to j, it is not 0. That means inner product of xi with itself is not 0. Inner product of xi with itself, what is that? It's the square of the length of x. How many of you are with me? Inner product of xi with itself. I'm assuming I'm given a set of non-zero vectors. Do you understand the notion of mutual orthogonality plays? Mutually orthogonal means what? Any pair of distinct vectors are orthogonal. The length of each vector is not 0. When the length of each vector is 1, they are called orthonormal. So orthogonality and orthonormality. I want you to distinguish these two. So I have a collection of vectors, xk. Each of xi belongs to Rn. So each vector is a n vector. I have a collection of k vectors. There are two possibilities. One is mutually orthogonal. Another one is mutually orthonormal. So what does it mean here? Inner product of xi with xj is equal to 0 for I not equal to j is not equal to 0 when I is equal to j. In here, this same property holds good. Xi, xj is equal to 0 for I not equal to j, but inner product of xi with xi, that's equal to 1. Here we say simply not 0, but say it's 1. So what does this mean? The length of each vector is 1. So what is an example of a set of vectors that are orthonormal? The standard vectors. So if you consider R3, I have E1 is equal to 1, 0, 0. I have E2 is equal to 0, 1, 0. I have E3 is equal to 0, 0, 1. You can verify. Each vector is a length 1. Any two vectors are mutually orthogonal. So that is a collection of mutually orthogonal vectors. Are you all with me? That's right. And when do I say they are A conjugate? Xi transpose A, Xj is not 0, is equal to 0 when I is not equal to j, and is equal to the norm of that when I is equal to j. This is for any A that is symmetric and positive definite. And please understand, this definition comes from here if A is identity. You're all familiar with identity matrix, right? That's right. Multiply any vector by identity matrix, it remains itself. So when A is an identity matrix, the energy norm becomes 2 norm. How many of you are with me? Come on, guys, please. Raise your hands. How many of you, if I say ask a question, how many of you are with me? Either like this, if you don't want to raise your hands. So how many of you are with me? Good. Then the notion of linear combinations. How many of you have heard of linear combination? We study before the exam and we forget after the exam, right? That's right. But we will see the linear combination being applied when we come to data assimilation. It plays a very fundamental role. So what is the idea here? I have a set of k vectors in Rn. Each vector has n components. If A1, A2, A3 as real scalars such that y is equal to, look at that now, A1 times x1 plus A2 times x2 plus A3 times xk, ak times xk. So this is a Saxby operation. You remember scalar multiplication of a vector plus a vector. So I create, there's a vector, I create a new vector, to that I add another vector, to add another vector, A1, A2 are constants. So what is an example of this operation? When all the AI is equal to 1 over k, I compute the centroid. You remember that? In physics, we compute the centroid of an object, set of objects. So if I have unit mass at positions x1, x2, xn, what is the centroid of the collection? The average. So computing the average of a collection of vectors is an example of a linear combination, where the weights of the linear combinations are equal to 1 over k, where k is the total number of vectors. So that's an example of a linear combination. So I talked about linear combination. Now I have to talk about what's another important property called linear dependence and linear independent. You remember my friend this morning talked about statistical independence. Two events are said to be statistically independent if the probabilities of those two events happening together is the product of the probabilities. So events can be dependent or independent. Computing the probabilities of independent events as product is a lot easier. Computing the probabilities of events that are dependent on each other is much more complex. So there we talk about statistical independence. Here we are talking about geometric independence. So what is the concept of geometric independence? Two vectors are said to be geometrically independent. I want you to get the basic idea. Two vectors are said to be geometrically independent if the angle between them is not 0. That's the basic idea. When the angle between them is 0 means what? It's collinear. The angle between the two vectors can vary from 0 to 90. When it's 90 is orthogonal. The larger the angle between them, more independent they are. The smaller the angle between them, more dependent they are. So dependency and independency depends only by varying the angle between the two. So orthogonal vectors are truly independent. But I'm not going to create a gradation of independence. Are you with me? So two vectors are said to be independent if the angle between them is not 0. If the angle between them is 0 means collinear. A collection of vectors is said to be linearly independent if no pair of vectors is collinear. Are you all with me, please? And how do I state that? How do I make that statement mathematically? Yeah, that x1, x2, xk are said to be linearly independent. The only way I can create a 0 vector out of that is when all the coefficients are zeros. If I can make the sum of a product of a scalar times a vector plus scalar times a vector, scalar times a vector, and create a non-zero vector means what? That non-zero vector depends on all the things. If I can create only the 0 vector, they are linearly independent. So that's the concept of linear independence and dependence. Yes, so in some textbook they define dependence first and then say independent is what is not dependent. In some textbook they will say independent, what is dependent is what is not independent. They are complementary of each other. This is a geometric independence as opposed to the statistical independence or probabilistic independence. Are you all with me? That's right. Now I'm going to go into another important concept that's called the span of vectors. Let me give you some quickly basic ideas. So suppose I have a set S which has two vectors. And what are those? This is E1, this is E2. So span of this vector S is a set of all linear combinations of vectors in that. So what's the set of all linear combination? A times E1 plus B times E2 for all A, B belonging to real. So what is A times E1? That's A. What is A times B2? E2, B. What is this? This is AB. A is any number, B is any number. So what does it mean? It's the whole space. Do you get the idea of the span, please? Come on, guys, you forgot. Nod your head. It's good for your neck. I don't want you to have a stiff neck after the class. You get the idea now? What is the space I can span? So what does it mean? Every vector in this space can be expressed uniquely as a linear combination of these two guys, E1 and E2. So E1 and E2 are two linearly independent vectors. The span of a two linearly independent vectors is a space of vectors that can be expressed as a linear combination of those two vectors. In this case, it happened that these two vectors are orthonormal. Suppose I get Oh, 1, 0, and 1, 1. So what is that? This is standard basis. So 1, 0 is this. So this is the vector x, this is the vector y. This is the vector y, this is vector x. Now do you believe that every vector in the two-dimensional plane can be expressed uniquely A times E1 plus A times x plus B times y? Come on, guys. That's right. Therefore, the span of these two vectors is the whole space. The span of these two vectors is the whole space. So if you have two linearly independent vectors, no matter what they are, that span is the whole space. All of you? But we are used to the span 1, 0, 0, 1. That's called the standard basis. So in this case, what is the x-axis? This is the x-axis, that will be the y-axis. So the axes are oblique as opposed to axis being orthogonal. I can do the geometry with the oblique axis as well as with orthogonal axis. When I do orthogonal axis, the geometry becomes simpler. When I do oblique axis, it becomes a little complex, but I can still do it. All of you? I'm looking at the way the heads are being nodded. I sometimes feel like the puppeteer show, remember? The puppeteer show, he can pull the strings. No, I don't want to pull the strings. I want all of you to have an individual response that is cognizant by each of you. So, how many pair of distinct linearly independent vectors I can have in 2 dimensions? Infinitely many. So there are infinitely many bases. There's only one orthogonal basis, every other basis is oblique. Oblique basis is one where the vectors don't have an angle that is 90 degrees. That's it. So span, the span of any 2 vectors is a vector space. Generally, so in this particular case, what's happening in here? I am working in the n-dimensional space. I'm only given k vectors in n-dimensional space. So if S consists of k vectors in n-dimensional space, what is the maximum number of linearly independent vectors I can have in n-dimensional space? N. The number of linearly independent vectors I can have in 2 dimensions is 2. If you have a third vector, I can always express the third vector as a linear combination of this, no matter where they are. All of it may basic geometry. I'm trying to convert the basic geometry into analytic geometry. That's what I'm trying to do. And that's what vector space theory is all about. So if I'm working in an n-dimensional space, if you give me a set of k linearly independent vectors, if I consider the span, what is the dimension of the vector space called the span? Is k. So it's a k-dimensional subspace of the n-dimensional space. I will give you an example. I hope you are with me. So I have 2D. If I have a set S is equal to 1, 1, what is the span of 1, 1? It is a set of all points in that line 1, 1. What is the dimension of the space? Is 1. This dimensional, one-dimensional space is embedded in a 2-dimensional space. So that's a subspace of the 2-dimensional space. Set, subset, space, subspace. All of you? That's right. Now the notion of basis and dimension, which I have already sort of alluded to. If B is a finite subset of a vector space. So a vector space has infinitely many vectors. You remember that? That's right. So I'm going to pick a subset. I'm going to pick a finite subset. Subset, finite subset, infinite subset. I'm interested in picking a finite subset. So every vector x in V can be obtained as a linear combination of vectors in B, then B is called the generator for V. Just like we saw, you remember? Previously we just saw that there are 2 generators, S1, which is 1, 0, and 0, 1. Another one is S2, which is 1, 0, and 1, 1. The span of S1 is a whole space. The span of S2 is also a whole space. The generators are different, but the space that they generate is the same. Do you all see the difference between space, generators, dimension, subspace? That's right. These are all the terminologies you need to know. So the set of vectors in B are linearly independent, then is called the basis. The span of S is V. If Vi is a unit vector where the ith element is 1, 0 elsewhere, that's called the standard basis. Hey, that's what we use generally, right? That's right. The number of elements in the basis is called the dimension. So this is the basis, there are two. This is the basis, there are two. So the space generated by them is of dimension 2. So you need to know what is the dimension of the space in which you're working. It's a two-dimensional space. Exercise. This is the most important part for me. I want all of you honestly to put your pencil to the paper. Are you with me, please? I'm going to give you a couple of minutes for you to be able to write this problems in your paper. X plus y square plus y plus 2 times x square plus y square. This is the typo. Verify the triangle inequality for 2 norm, 1 norm, infinity norm. Prove that x transpose y is the product of the two vectors when the vectors are parallel. When the vectors are parallel, what does it mean? The angle between them is 0. What is cosine of 0? 1. So how do you test two n vectors are parallel? Compute the inner product. How do you test two vectors are orthogonal? Compute the inner product. Are you with me? How do you find out the angle between two vectors in 100-dimensional space? Compute the inner product. Compute the norm. Use Cauchy-Schwarz inequality to get the angle between the two. How do you test the given vectors are linearly independent? Compute the angle between the two. Are you with me? How many of you are with me? I'm giving you algorithms to answer questions. All of you with me? That's right. I'm giving you algorithms to answer questions. Let x be this vector, compute the 1 norm, 2 norm, infinity norm, and verify all the relations between the two norms. You remember the inequalities I gave you? So let me tell you the trick to learn mathematics. First, you need to understand what it is. Then you need to verify that indeed my understanding is right. Once you understand, once you verify it is true, then you need to ask a question, why is this true? All of you? I don't know how you do it, but it's quite some time since I was in graduate college, but I still do the same way. First, need to know what it is. I want to verify the truth of this by examples. Once I'm convinced this is true using examples, wow, it made a believer out of me. Then I want to ask myself the question, why is this true? What makes it true? What's the proof that I can carry to be able to verify it is true? All of you? All right. Data assimilation is half mathematics, half domain-specific knowledge. Are you with me? I just completed a PhD thesis with a student in Bombay IIT on hydrology. He was interested in trying to predict the flow in a stream. The hydrologists take care of the model. Once the model is done, observations are given, I take over. So they understand some data assimilation, I understand some hydrology, but we separate. Oh, this question can be answered only by hydrologists. This question is a dynamic data assimilation problem. Only a data assimilation person can answer this. Are you with me, please? So I work with meteorologists, bioengineering people. Wherever there is parameter estimation, wherever there is model, wherever there is observation, there is data assimilation. Are you with me, please? So it's a combination of domain-specific knowledge, but tools from mathematics. What are the areas? I will state it once more. Vector space theory, matrix theory, the multivariate calculus, optimization theory. We are going to see the role played by each of these components when we start doing the problem. How much time we have?
We have 20 minutes.
Huh?
20 minutes more?
20 minutes, good. Oh gosh, I finished earlier than I thought I will. I was expecting a lot more questions, but that's all right, I'm not complaining. Any questions, please? You all see the need for this? How many of you see the need for this? How many of you have started reading papers in data assimilation? That's right. The lingo, the language that they express, you need to know what they mean when they say this, when they say that, and so on. And that's where this vocabulary and the properties are needed. With me? So I'm going to spend the next 20 minutes until he rings the bell on certain aspects of matrices. Tomorrow morning, I'm going to start bright and early with data assimilation problem. And I will develop the problem and then I will stop. Hey, I need to be able to answer the matrix question. What is that? Come back. I need to understand the optimization question. Do that, come back. I need to do this question, come back, do that. So I'm going to do the mathematics in the context of solving a given problem. So you will get a contextual aspects of it. And you will see many of the ideas that I have talked about in today's class will come into play when I start talking about the first exercise in data assimilation. All of you? Any questions, please? Good. If there are no questions, I don't want to keep looking at you. You don't want to keep looking at me. We all know each other very well by now. So I'm going to go to the slides. Quickly refresh the basic concepts from matrices. When will they have access to these videos? For these slides?
Already this is online. We are going online.
Okay.
In YouTube.
Oh, it's on YouTube. Okay, good. So if you have not taken down, if you have not taken pictures of the problems, please do. The best way you help yourself is to solve problems. You remember the Bayesian he talked about? What was your prior knowledge about data assimilation before you came into the lecture? That's a prior knowledge, right? He called it likelihood. That's also called conditional expectation. I'm sorry, conditional distribution. You are learning new knowledge. New knowledge revises the prior. You get posterior. After every lecture, you should not be the same person you walked in before the lecture when you go out of the lecture. Are you with me? You have to promise that to yourself. Am I a changed person? Did I learn something new? What did I miss? Why? Yeah. What's that?
When we talk about span of linearly dependent vectors, is there any use speaking about span of linearly dependent vectors?
I thought I was giving you a feeling. Maybe you didn't get my feeling. I'm going to say it once more. I'm glad you asked the question. Good, good. So let's take, for example, the simple orthogonal basis, okay? So I have to write this in a set. I'm lazy, I don't want to write too many things. Well, I am given two vectors. Are these two linearly independent? Linearly dependent vectors? Oh, if there are, okay, good. Let me do that. Is the third vector linearly dependent of the previous two? That's right. So what does it mean? The third vector 1, 1 is equal to 1 times E1 plus 1 times E2. So if the third one is already a linear combination of the first two, the span of the 3 must be equal to the span of the 2. Is it yes? Yes. That's right.
So is there any point of talking about, because when we talk about this definition of span, we don't explicitly mention that.
No. Let K be a subset of a vector space. Let K be linearly independent set of vectors from V. Then you call the span of it. Are you with me? That's right. So the span and the linear independence go together. I have just given you an example. The third guy is a part of me. If you're a part of me, you don't have to worry about him. So drop all those guys who are linearly dependent. Distill the base, the minimum linearly independent set. They are the king. Are you with me now? Good. I have a theory called AHA theory. You may have heard me say in other lectures, I'm going to say it once more. On a hot summer day like today, when somebody gives you a very nice ice cream cone, you take the first sip. What is the first reaction? Isn't that what you react? Please eat an ice cream and see what your reaction is. If you didn't say, a good cup of coffee, a good taste of a sweet, a good cuisine, the first time you test it, what is the reaction? Wow, good. Are you with me? When you go to a concert, how do people enjoy the concert? Wow, wow, wow. Do they say that? How many of you go to concerts? In classical music concert, everybody, when they sing something, when they put some brigas, we say, wow, wow, aha. The wow is aha. So to me, life is a collection of aha moments. Are you with me? Like the time when I first enjoyed my ice cream. This morning when I enjoyed my first coffee. When I enjoyed my the good dessert this afternoon. Are you with me? Hey, you have to enjoy life. And how do you express you enjoy life? Wow, aha. Come on, guys. Generally, in India, we always try to use the word okay. Okay is dull. Okay means what? Is acceptable? No. Acceptable is not the right thing. It must be good. Aha, wow. You have an aha now? Say aha, buddy. Good, that's right.
Sir, I have a general question.
Absolutely.
Sir, in one of the paper I read that for the assimilation purpose, we are using 5 to 10% of all the available observations. So if we want to increase, we want to implement more number of observations.
If you want to use more number of observations.
Yes. In our assimilation problem. So there will be problem of computational cost.
Okay.
And yeah, let us first.
So what is the question? Are you passing a comment or asking a question?
Is there any algebraic approach or linear algebra?
We will. You bring.
We can handle dense observations.
Good. Generally, if you in data assimilation, different people work together. The observation guys, they only collect observation. Satellite guys, radar guys, instrument measurement guys, they dump you all the observation. The whole question is which one you pick, how do you use them, how do you decide? Are you with me?
Asking about observation because
you have to finish your question. Yeah, is the question finished?
No, sir.
Good, thank you.
Now I want to add something.
Yeah, I'm going there. I will answer the question more later.
Every assimilation cycle, we want to correct our background state by supplying the observation.
This guy is reading too many literature and he is throwing all the words. I will give life to every one of them what he says. He's not telling anything wrong. He's asking a right question. What is the question he's asking? I have a model, I have a ton of observation. Should I assimilate all the observation or should I pick a part of it? Why? How? Is that right? That's it. That's $1 million question.
And one more question.
What is that?
Problem of
Of course. That's what I'm going to answer. Have you finished now? Good. I just want to make sure I didn't stop you. I want you to finish your question before I start answering.
And one more question is there.
Why don't you let me answer the first question?
Actually, sir, I want to hear your insight on the perspective of linear.
Please understand, I'm talking about only linear algebra. I'm not talking about data assimilation now. Okay?
Yeah,
You are.
I'm adding linear algebra.
But you have to understand. You have to separate the question. You remember? So today's class is linear algebra. So today I'm going to ask you a question relating to linear algebra. I have lots of observation. Which one do you pick? Sure, that's a research I'm currently working on. I'll be happy to work with you. I'll be happy to talk to you. That's a beautiful answer for that. But hold on, I cannot mix with that. I'm eating breakfast now. It's not lunchtime. Are you with me? But it's your responsibility to ask that question again when I do data assimilation. Maybe tomorrow itself, tomorrow afternoon. Sure. Okay, any other question? Yeah. Huh? I think I didn't get the basis. What basis you pick the observation? No, I'm sorry, I apologize. You may have to use the one. Let the person talk. 1 second. This is not on. I can't hear.
Basis of a vector space.
What then?
What is the definition of basis of a vector space?
Basis of a vector space? Oh, I showed you million. Do you believe R2 is a vector space? What is R2? Set of all vectors in 2D. Is it aha? No. Why? You add any two vectors in 2D, you get a vector in 2D. Yes. You multiply any vector in 2D, you get a vector in 2D. You get any vector in 2D, take the opposite of it, add, you get a 0. Yes. So it satisfies all the axioms of vector space. R2 is a vector space, Rn is a vector space. You still don't have an aha. What is the definition of vector space? A vector space must satisfy condition C1, C2, C3. Condition 1, C1 talks about the properties of the sum. So you take two vectors, add two vectors, you get a two-dimensional vector. Are you with me now? You multiply a vector by a constant, you get another vector. You multiply a vector by -1, you get the negative of the vector. You add the negative vector to a vector, you get 0 vector. You multiply any vector by 1, you get the same vector. If you have two constants to multiply, a times x, b times a times x, I can do that. A plus b times xy. I'm glad she asked this question. I don't know how many of you have this. This is ax plus bx. A times x plus y is equal to ax plus ay. This is the distributive property. Everything holds good for vectors in R2. So R2 is a vector space. R3 is a vector space. Rn is a vector space. Is that an aha? That's right. I'm not forcing you. You have to say it yourself. You should be cognizant of what you say. That's right. So what is the basis for R2? I already gave you two bases. There are infinitely many bases. If you took any two vectors that does not have a zero angle between them, how many different vectors I can pick such that the angle between them is not zero? There are infinitely many. So there are infinitely many bases. But there's only one basis that is orthogonal, which is E1, E2. What is E1? E1 is 1, 0. E2 is 0, 1. Her head is nodding and the amplitude of the nodding is increasing. That means more and more aha. Is that right? That's right. Today's class is about linear algebra. Tomorrow onwards, we'll go to data assimilation. Are you with me? Any other question? So if not, let me quickly start talking about matrices in a few minutes. Instead of using the slides, I will use quickly my blackboard. There are so many different operations on matrices available. So what is that I need to do? I need to do everything that I did to vectors to matrices. So what is a set of matrices? What is the dimension of a matrix? What is the size of a matrix? What are the operations on matrices? Are you with me? With matrices, there are more operations than there for vectors. For vectors, to remind ourselves, what are the operations? Addition, subtraction, scalar multiplication, inner product, outer product. Norms, 2 norm, 1 norm, infinity norm, p norm, energy norm. Cauchy-Schwarz inequality, linear dependence, linear independence. I'm done. Are you all with me? So we need a similar thing for matrices. So when you approach mathematics, which world I belong to? Am I belonging to real algebra? Am I talking about complex algebra? Am I talking about vector algebra? Am I talking about matrix algebra? It is this ability to distinguish and compare enriches your understanding of the mathematical systems. So what is a matrix? A matrix is a two-dimensional object. It can have m rows, n columns. It is denoted by m by n matrix. Then this is called a rectangular matrix. When m is equal to n, that's a square matrix. Square matrix. A matrix has columns. A matrix has rows. A matrix has diagonals. I can slice the matrix column-wise, row-wise, diagonal-wise. What is my place? I can add two matrices. So let A be a matrix, B be a matrix, C be a matrix. I can add, subtract. Let us see. Everybody, I can have two matrices A and B. I can multiply two matrices A, B. How many of you know the rule, matrix multiplication? That's right. That's right. So I can multiply a matrix by a constant. I can take a transpose of a matrix. I can talk about a trace of a matrix. How many of you know the trace of a matrix? It's the sum of the diagonal elements of that. So trace is an operation, transpose is an operation, product is an operation, addition subtraction is an operation, multiplication of a matrix by a scalar is an operation. Determinant of a matrix. So in here I'm assuming A is square. Determinant of a rectangular matrices are not defined. If you have square matrices such that the determinant is not 0, then the matrix is called non-singular. If the determinant is 0, it's called singular. Then if I have a matrix, I can talk about the inverse of a matrix. If I can, A inverse, it's called identity. Identity matrix is subscripted n. So this is very similar to A times 1 over A is equal to 1. That we call reciprocal. Here we don't call it reciprocal, we call it inverse. For the inverse to exist, A must be non-singular. The determinant of A must be 0, must be not 0. Rectangular matrices do not have determinants. Then there are special matrices. Matrices can be symmetric. A is equal to A transpose, then A is called symmetric. And what is an example of a symmetric matrix? A, B, C, E, A, F, F, G, G. That's an example of a symmetric matrix. One is the mirror image of the other. What is the property of symmetric matrix? A is equal to A transpose. A is equal to A transpose. How many of you know all these concepts? Some people determine not to raise their hands. Please help me to help yourself. Self-diagnosis is the best diagnosis. Okay, and what are other matrix problems we are going to be able to solve? So one is called the quadratic function of A of x. So A is a matrix. So a matrix, this matrix is a real matrix. I'm going to say this matrix belongs to Rn by n. This is very similar to saying x belongs to Rn. If I say x belongs to Rn, x is a n vector. How many have heard me? Hey, there's a notation. There's nothing to understand. It's like in English, sit means sit down, right? Eat means you eat. In English world, when you learn English, do you understand it? No. So what does understanding means, English? Get the right usage. So I'm talking about the language of matrix algebra. All of you? That's right. The lingo of matrix algebra. In here, what is that? This is A belongs to R. Mathematicians are very clever people. If you're clever, you can be lazy. So they don't want to write too many things. Understand? So let A be a n by n real matrix. No, they won't say that. They will simply say, let A be this. Let A be a non-singular matrix, which is this. Short, sweet, but everything is contained, succinct. So you need to understand these notations. Yeah, I hope all of you know this is belonging to, right? That's right. So that's that. Symmetric matrix. Then the quadratic function. You remember where did we meet this? Energy norm. You remember that? Ah. How many of you remember that? That's called the quadratic function. So what is the quadratic function in one variable and n variable? The quadratic function in one variable, q of A of x, equal to A times x squared, is equal to A times x squared. Well, let me stop right there. So here, what is that? So let's assume A is R2, x is R2. That means x is a 2 vector, A is a 2 by 2 matrix, and A is symmetric. So what is this? This is x1, x2. This is A, B, B, C. This is x1, x2. All of you? Come on, guys. That's what this one is. So what is this? Multiply this. Make sure you understand this is 2b x1, x2 plus c x2 squared. So this is the polynomial of degree 2 in single variable. This is a polynomial of degree 2 in 2 variables. This is a homogeneous polynomial of degree 2 in 2 variables. But if I have ax squared plus bx, ax squared plus bx plus c, say all these things, they share the same property. They are all 2 second degree polynomial. The first one is homogeneous, only 1 degree. Second degree, first degree, and a constant. Second degree, first degree, and a constant. Everybody with me, please? So what is this? This is the homogeneous polynomial in 2 variables with respect to a symmetric matrix. Are you all with me? I want you to verify these. You may look at an expression 1,000 times, but unless you do it, you don't get it. I want to tell you something. Can you play golf by reading a book? Can you play cricket by talking about it? Can you cook simply by talking about it? Can you swim simply by talking about it? To learn cooking, you have to burn your finger at least once. To swim, at least you have to drown once. Understand? Doing mathematics is no different from swimming, doing cooking and any such thing. You learn by doing. You learn by doing. Please do. That's why exercise is so fundamental and important. So this is a quick introduction to some of the things that are coming to matrices. Tomorrow morning, bright and early, I'm going to start with the very fundamental basic data assimilation problem. When we go into dynamic data assimilation problem, we will address that question. Please hold on. Please bear with me. So 1 or 2 more minutes. Any questions? How many of you have an aha on linear algebra, that portion we covered today? That's right. Please enjoy the evening. Bangalore is nice, except that you can't go anywhere here. So if you get bored, please work on the problems. And if you have any questions on the problems, I will devote some time toward the end of tomorrow to help you solve the problem. With that, we will close today's session. We will meet. Please take over.
Yeah, thank you, Professor Varahan. So we don't have any more sessions today. Tea is arranged outside, so we can have the tea and go back to there. Tomorrow morning, 9:30, we'll start the session. So we'll continue the same discussions in the same lecture hall. Thank you.